Didn't realize you were ready.
No, you're good. It works out perfect. So, but yeah, Dorian, you can just talk to me and
Yeah, sure.
ignore these
Okay.
cameras as best
Perfect.
we can.
Perfect. Yep.
But yeah.
Yep. Yep.
Screw this up.
Yep.
There we go. Okay, so first of all, Dorian, just so I get it right, can I get you to say and spell your first and last name?
Okay. Dorian, Dorian, Garrick, Garrick.
And your hometown is?
My hometown, where I work now, it's in Hamilton in the Waikato in New Zealand. Yep.
Perfect. So, Dorian, can you give me just a little bit of your background and just kind of how you got into all the EPD research?
Sure, yeah. So I did an ag degree, and I was very fortunate that one of my lecturers, one of my faculty, had just finished his PhD at Cornell on estimating heritabilities and genetic correlations and predicting breeding values. So I didn't know it at the time, but my undergraduate education was actually more like a postgraduate education in animal breeding. I went on after I graduated, and I worked in evaluation of sheep and pigs. So I applied what we now know as the BLUP methods to sheep and pigs back in New Zealand about 35 years ago. It was probably some of the first applications of those animal models in those species. And then I had the opportunity to study at Cornell and do a PhD where I worked on theoretical problems as well as doing work on both beef cattle and dairy cattle. And my beef cattle work was mostly with Simmental data, looking at differences in heritabilities between growth traits measured in male calves versus female calves. And since then I've continued to work a lot in prediction and genomic prediction using genomic DNA information and getting it implemented in industry.
So to kind of backstep that, walk me through some of the history of EPDs and genomics in the beef industry.
So, sorry, it was a bit hard to hear that for the truck.
Talk about the history of EPDs in the beef industry.
All right, okay. Right, okay. So the concept of predicting EPDs is something that goes back a long way. The technology was really developed around about the time of the Second World War, and it was pretty rapidly adopted after that time, probably coinciding with the establishment of the Beef Improvement Federation, where pedigree and performance records would be used to try and come up with an idea of the value of an animal as a parent. So instead of thinking of, do I like the look of this animal or the weight of this animal, what we were interested in is if I use this animal as a parent, will its offspring be average or above average or below average? And the EPD system is just a complex statistical way of combining all the information we have, and that information is contaminated by nuisance effects, like some animals are born earlier than others. Some have mothers that are middle-aged and others have mothers that are young, and that changes their performance. So that's not anything to do with the genes of the calf. So we need to adjust for all those environmental effects, and then we need to combine all the information on relatives. If we know an individual is above average and its offspring above average and its other relatives are above or below average, we can combine all that information. So the EPD system is just a very complex statistical formula for taking raw data that you observe on a farm, removing all the nuisance effects and combining all the information from relatives to come up with the most accurate prediction we can given the data available. It won't be perfectly accurate unless the animal's been progeny tested with lots of offspring, but it's the most accurate prediction we can get given what we have observed on the animal and its relatives. Yep. So it was recognised again round about the Second World War that if you selected chickens on their blood type, you could change their disease resistance. And they recognised that Their blood type itself had nothing to do with their disease resistance. They just imagined that the gene that controlled blood type must have existed nearby to a gene that controlled the disease resistance. So for decades we've had the idea that if we could somehow mark or trace the genome fragments, we could come up with an EPD for every fragment of the genome. So instead of thinking of an EPD of a bull or a cow, we could think of the EPD for each piece of its genome. And then if we were to look at a new calf or even an embryo and genotype it and see which fragments it inherited, if it had positive ones, then we would think it would be above average, and if it had negative ones, it would be below average. But since they have 30 pairs of chromosomes and many fragments, what we do is we sum up often 50,000 pieces of information, many of which are positive and many of which are negative, to come up with an EPD of the animal, just like a conventional EPD, but it's based on tracking those chromosome fragments. And the nice thing about it is that if we have two calves that, say, had the same mother and father, like from embryo transfer, based on pedigree information, we would both predict them to be parent average. Now, in real life, we know one of them will be better than the other, but we don't know which one. With genomic prediction, at that young calf stage, we can predict which one would be better than the other. And again, the prediction won't be perfect, but it will be better than parent average.
Getting that much more detail in our predictions each and every
Yep. 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 So there's two aspects to implementing this at industry level, and one is that we have to be able to characterize, see the fragments that are present in our breed, and that means we've got to genotype a lot of individuals. And then we have to use that historical information to characterize all those chromosome fragments that those individuals carry. And that's what we call developing a training population. And so if you want to do genomic prediction, you can't do it until you have first characterized a training population. And that is an expensive exercise because it means you have to genotype a lot of existing individuals, and that genotyping won't make their predictions any more accurate. What it will do is make predictions of future individuals, future selection candidates, more accurate. And so what we've seen happen, say, in Salers is they have now characterised a sufficiently sized training population to be able to work out the value of those fragments. So they are now in a position that if a new calf was born, we could come up with a prediction of whether that calf would be better or worse than average. Now that prediction will become much more accurate if the size of our training population increases. So as more animals are genotyped, the accuracies should get better and better.
One second, real fast. I'm going to flip that microphone around. I'm catching just a little bit of wind.
Yep.
Sorry about that.
My phone was just ringing. I don't know who that was. It's probably somebody. Oh, people at the lunch wondering where I am.
Oh no, I'm sorry. Oops.
I'll just.
There we go. Sorry about that.
I don't know if you were going to ask about low density and high density, but will you tell them that?
If you want, yep.
So yeah, talk to me about the difference between the high density and a low density test.
Okay, so the genome itself is stored in chromosomes, and cattle have 30 pairs, and each chromosome has 100 million base pairs roughly. So the genome of a beef cow or a beef calf is 3 billion pieces of information. And we could observe all 3 billion if we were to sequence the animal in their entirety, but that's both expensive and time consuming to do at the moment. So what we do instead is we just measure markers more or less evenly spaced across the genome. And the most common density that's used is called 50K, so they mean 50,000 markers spread across these 30 pairs of chromosomes. So it's about 2,000 markers on each of the chromosomes that have about 100 million base pairs. So it's fairly sparse, but it's enough for us to track the inheritance of chromosome pieces from one generation to another. Now, it is more expensive to do higher densities like 700K. Sometimes it's cheaper to do lower densities, but it's a little bit like buying your first computer. Every year the computers become more powerful, and sometimes more powerful and cheaper at the same time. So now there are a whole range of different chip densities available. And we used to think of low density being 3K or 8K or 10K. Today low density is probably 25K, and most of our genotyping is done at higher densities, typically around about 50K.
So that's for your average Celera producer, commercial your average seed stock Celera producer. Where should they be targeting? Should they be targeting that 50K that?
Yeah, so there are economies of scale when you negotiate into contracts, and some people like the idea of using lower density maybe on their young animals, and then if they choose them as parents, doing them again with a higher density. But sometimes it's much more cost effective just to do everybody at a density of 50K right from the beginning. And 50K today is not much more expensive than the lower densities, and sometimes not any more expensive than the lower densities. So yeah, I would be targeting around the 50K, maybe 30K if it is substantially cheaper.
Talk to me about what Celera breeders can kind of expect from once more and more of this data is coming in. What can they expect from? Will their EPDs start to shift? Will they see a change in accuracy?
Yep. So EPDs are the best prediction given the information you have available. And what we know is that if you observe more information on an animal, it's equally likely to go up an EPD or go down an EPD. So yes, we will see animals shift. They'll shift in both directions. But we very seldom get somebody complaining about an animal that moved up, but everybody tends to complain about an animal that moves down. So often the complaints you hear about animals that have moved down, but part of the validation process is to look at how they've changed and make sure that they have moved up just as often as they have moved down. The thing that should be more apparent is that the accuracy should always increase. So bringing in the genomic information should always increase the accuracy. But if the animal already has a lot of progeny, for instance, the accuracy is probably quite good, and the genomic information is not going to increase it very much. The accuracy will go up most for the animals that have the least information. So if you had a newborn calf and you have no records on it, maybe not even any pedigree, that's where you would see the highest lift in accuracy. If you only had parent average, you would see a big increase in accuracy. But if you've measured birth and weaning and yearling weight, then its predictions for growth will go up, but not by as much as they would before you had that data.
How important is that phenotypic data that's coming in on weaning weight, birth weight? And do you see us ever get into a point where we don't need that?
Yeah, the phenotypic data is critically important because the phenotypic data is what comprises our training population. And we want the training population to get bigger because that will make it more accurate. But we also want the training population to be as closely related as possible to our selection candidates. So if you just did a training analysis, at a particular point in time, and then you tried to do predictions without phenotype in successive generations, you would find the accuracy of the predictions would slide each subsequent generation. But if you continue measuring the phenotypes, then you should see the accuracy increasing because it's from close relatives and your training population size is getting larger.
So I think there's, and tell me if I'm wrong, there's kind of a trend in certain in some breeds and some breeders who they just want to focus on the genomics, but having that raw data is still.
Yeah, so from a selfish perspective, yes, if everybody else collected phenotypes and I stopped, that would be better for me if collecting the phenotypes is costly or labour intensive. But from an industry point of view, that's not the kind of behaviour we want to encourage.
Now, talking on the Solaire side, you've got a much smaller breed compared to maybe the Angus Association. But what benefits do they have on being a smaller breed and having that new baseline for genomics? What's the value?
Well, I suppose the benefit from being a smaller breed is that whatever size your training population is, if it's say 2,000 animals, it's a much larger fraction of the breed than it would be in a very large numbered breed like say Angus. But the other thing that matters is the effective population size of the breed, and that's related to how inbred it is and how much the inbreeding is increasing each year. And that's really controlled by how many sires are used each generation as fathers of the next generation. And if the population has a smaller effective population size, then the genomic predictions will be more accurate.
Are there any disadvantages to being that smaller breed, fewer genotypes? Or is it just
Well, the disadvantage of a smaller breed is that it's hard to get the critical mass to negotiate cheap prices on chips, for instance. Angus can go in and guarantee they'll do 250,000 animals in the next year, say, whereas a small breed, they're talking about hundreds or thousands. So it's just the economies of scale that are no different from the difference between having 50 cows in your herd or 500 cows in your herd.
Where do you see, what do you expect to see help the Solaire breed really take off here in the future genetically? What's the value of these genomics and how's it affected?
Yeah, the popularity of a breed is partly to do with how good it is and how much they improve it, and partly to do with how it's marketed. So is the Solaire's breed going to take off by introducing genomic prediction? Well, people like myself don't control selection. What we do is we rank the animals. It's the people that own the animals that decide if they're going to believe in that information, if they're going to invest in the genotyping. So the responsibility, the opportunity, all of those things sit with the collective actions of all of the individual breeders. So the important point is that they are educated as to what's being done and how it's being done, so they can decide whether it's going to improve their businesses by widely adopting it or not.
Sherry, am I missing anything?
That's
Dorian, is there anything that we're missing?
No, that's all good, thanks.